Last time we talked about electric force and we modified our grade 11 version of the electric force formula for a more generalized version. So we ended up with electric force equals K times Q1 times Q2 divided by R squared. Okay, and so that makes it just more applicable to all situations. However, we are not going to actually spend our time focusing on solving problems about electric force. Rather, we're going to move forward to energy. What we're really going for here is how does work and energy apply to electricity? So we're going to look at parallel plates. Now I've drawn a set of parallel plates over here. I drew them horizontally, so we're not trying to think about gravity in this case. Okay, so we're ignoring gravity for this type of situation. So let's think about this for a second. If you would put a negative charge right over here, there's a negative charge. What it would want to do is move this way toward the positive plate, right? Because a negative charge will be attracted to the positive plate. Opposites attract. You can also think that it will move the opposite direction of the field. In order to move this charge toward the negative plate, if we wanted to go the other way, work would have to be done to get it there. Okay, so work is force times displacement, right? So in order to move it this way, you would have to exert a force this direction over a displacement in order to get it to that negative plate. Now you can kind of think about it like you would be compressing a spring. As you push this negative charge toward the negative plate, it's going to want to move the other way more and more and more. So this negative plate is going to be pushing harder on this negative charge in order to get it to move this way. Okay? And so it's almost like you're compressing a spring when you're moving it that way. You're moving it against the field, and that would be called work. So when you move this charge over here, you would be giving it something called electric potential energy. Electric potential energy. So it wants to, let's say, fall back this way toward the positive plate, because that's what the electric field would be telling it to do. But by moving it over here, you've stored energy in the charge because of its position, and that's called potential energy. And so our formula for electrical potential energy, or electric potential energy, follows this pattern that we've established using work. Work is force times displacement. So if we're doing work equals force times displacement, in this case, this is electric force that we're talking about, Fe. And Fe is Q times E when you are in a uniform electric field. Now, the situations that we're going to be dealing with here are all parallel plate situations, and so we can use that simplified version of the force formula because that field is a uniform field, okay? And so we can put in here Q times E, that's electric force, times displacement. So that's the work done to move it to this position. Now at this position, you have given it a certain amount of electric potential energy. And so the work that you have done is the electric potential energy that you've given it. And so our formula for electric potential energy is going to be like this, E sub E. So we've been using large E for energy, and the subscript E is electric potential energy, equals Q times the field, so it's charge times the field times displacement. That brings us to a related concept, potential. So we've talked about potential energy. We're going to bring in a new concept, but related, called potential. Okay, so when we were looking at this charge over here, we said that this charge in this position has more potential energy than this charge in this position. Okay, this charge, it's like it's compressed the spring more. It wants to be pushed away to this side of the parallel plate setup. Okay, it wants more than this charge to do that same thing. And if we look at another charge right over here, it has no potential energy, no electric potential energy, that is, because it's already in the position of lowest potential energy. Okay, and that's where the idea of potential comes in. So potential energy is a characteristic of a charge or of an object. So those negative charges in the parallel plates, they all have potential energy of some kind. But if we look at where they were, so this position right here, this position does not have energy. The position has potential. Okay, so this charge here, it has electric potential energy, EE. This position over here, it has electric potential. Okay, so at this place of potential, if you would place a charge there, it would have potential energy. So this place has a certain voltage, okay, potential difference. This charge over here has a certain amount of electric potential energy, and at that position has a certain amount of potential. Same thing with this other one. The potential right here, it has no potential there, okay? And so when you place a charge there, it has no potential energy. So potential energy is a characteristic of an object, or in this case a charge, and potential is a characteristic of a location. Let me give you one more example. So if you were going down a water slide, here's the water slide. Oh, this is an intense water slide. There you go. So you're going down a water slide. This is you. So excited. You're going to go down this water slide. At this very top position over here, this level, you have a whole lot of potential energy, right? Because you have been raised high above zero height. This is zero height down here. So over there you would have no potential energy, no gravitational potential energy. Up here you have maximum gravitational potential energy. And as you go down the slide, you lose that gravitational potential energy, which is converted into kinetic energy. So you speed up as you're going down the slide. So we can look at the different positions on the slide. Up here has maximum potential. Down here, the amount of potential is decreasing, okay, because the location is changing. So at this position, it has less gravitational potential there, and when you are there, you have less gravitational potential energy. So potential is a characteristic of the location. Potential energy is a characteristic of the object at that location. Okay, and so the formula that we have here can talk about electric fields in terms of potential, okay, in terms of the location. So electric field strength depends on how quickly the potential changes, change in V or change in voltage, over a certain distance. Okay, so if the potential difference between these 2 points is 1 volt over 200 meters, that's a pretty weak electric field. Okay, but if you have a very strong electric field, if you have a change in potential or a change in voltage of 100,000 volts over 1 meter, that's a much greater, a much stronger electric field. Okay, and so we can measure electric field strength not just in newtons per coulomb anymore, but we can measure it in terms of volts per meter. So this E over here, this is still electric field. This change in V over here is potential difference. I'm going to abbreviate it. Potential difference. Okay, and we can also refer to potential difference as voltage. And voltage, guess what, is measured in volts. Okay, and this change in D part over here, this is displacement. Now, we can think of that displacement in a couple different ways. So we can think of it as the distance a charge is moved in an electric field and what the potential difference is between those two positions, or we can think of it as the separation between 2 points. Okay, so if you have 2 plates that are separated by a few millimeters, then that change in D there would be that few millimeter separation between the plates. We can also combine these two equations that we've just made to write electrical potential energy in terms of voltage or in terms of potential difference as well. So if we look at, let me grab a different pen. If we look at E equals potential difference divided by separation or displacement, and we also look at electric potential energy is equal to Q E D, then we can see we have some things in common here. We have an E and a D here, we have an E and a D here. And if we rearrange this top formula just slightly, we get voltage difference or potential difference is equal to E field strength times displacement or times separation. And so this is the same as this. And so then we can just sub in our change in V there. So then we get electric potential energy. Let me write this over here. Electric potential energy is equal to charge times potential difference. Okay, now we're going to write that a slightly different way over here, though that is a useful piece of formula as well. We're going to write it in terms of potential difference equals electric potential energy divided by charge. Okay, now we said that the potential of a pair of parallel plates is a characteristic of the location, and if you would put a charge there, then it has potential energy. So it should make sense that if you divide out the charge from the potential energy, you get potential. Okay, so potential is energy divided by charge. Now we're going to do a few examples to show how this works practically. It takes 0.05 joules of energy to move a 0.2 microcoulomb charge from point A to point B. What is the potential difference between these 2 points? Okay, so it tells us what happens with the charge. It tells us how much electrical potential energy it gains or loses moving from one point to another. And now it's asking us about the field itself. What's the difference between the two locations? Okay, and so we are given the charge, (0.2 microcoulombs). Micro is times 10 to the negative 6, so 0.2 times 10 to the negative 6 coulombs. I realize that that's not generally how scientific notation goes, but for our purposes it doesn't really matter if it's written correctly. We know that the electrical potential energy that was used was 0.05 joules. And it's asking us for what's the potential difference between those 2 points. So what's the voltage? Okay, Q, E, and V, or Q, E sub E, and V. So we get voltage difference is equal to electric potential energy divided by charge. Potential difference, or voltage, is equal to 0.05 joules divided by 0.2 times 10 to the negative 6 coulombs. And so the potential difference between those 2 points is 250,000 volts. That's a lot. How much potential energy is lost when 25 coulombs of charge goes through a potential drop of 120 volts? So let's just take a look at what's happening here. Let's make this positive and this negative. So a potential drop of 120 volts would be like if a negative charge over here moved this way to another point between the two, and the difference between these two positions over here was 120 volts. We're looking for what is the electric potential energy, E. And that's equal to Q change in V. Electric potential energy is 25 coulombs times 120 volts. So the amount of energy that was lost, potential energy that was lost from that position 1 to position 2 was 3,000 joules. $3,000 was lost. Okay, but it didn't just disappear. Remember, energy gets transformed from one type to another, and so that means that charge, though it lost 3,000 joules of potential energy, it gained 3,000 joules of kinetic energy. And the last one I want to do with you is this. An electron, one electron, accelerates from rest through a potential difference of 250 volts. How much electric potential energy did it lose? We're supposed to answer that in joules and electron volts. That's what this is. EV. That's electron volts. And despite its name, it is not a measure of voltage at all. It's a measure of potential energy. It's like coulombs and ECs are both measures of charge. Joules and electron volts are both measures of potential energy. So we're going to use the same formula that we did before. Electric potential energy is charge times potential difference. One electron has a charge of 1.6 times 10 to the negative 19 coulombs. And our voltage difference is 250 volts. And so that gets us an electric potential energy of 4.0 times 10 to the negative 17 joules. Okay, now here's the purpose of electron volts. Notice that we used coulombs in here to figure out what the electric potential energy was. If instead of using coulombs in here, we would use ECs, then we would get electron volts. Okay, so we could also do the same calculation. E sub E is equal to 1 EC times 250 volts, which is equal to 250 electron volts of energy. Okay, so the purpose of electron volts is for using ECs instead of coulombs. Now, you can also do the conversion at the end if you would like to. So if you took this joules and wanted to switch it into electron volts, you need to know that 1 electron volt is 1.6 times 10 to the negative 19 joules. It's just like how 1 EC is 1.6 times 10 to the negative 19 coulombs. So we would just take this 4.0 times 10 to the negative 17 joules, and we would do our conversion. So if I want to get rid of the joules and change it to electron volts, I go 1 electron volt is 1.6 times 10 to the negative 19 joules. And when I do that division, I get the exact same thing. I want to give you an analogy that might help you understand voltage a little bit better. So what we have here is a set of parallel plates, but parallel plates aren't just these freestanding pieces of metal that somehow become charged. They are connected to a battery somehow. So we're going to connect these two plates to the two poles of a battery. Here's our battery. Okay, and when you connect them to the poles of a battery, then they obtain the charge that the poles have. So now let's say that this one becomes negatively charged, and this one becomes positively charged. Now, this is not really a useful setup for anything, except one thing. That's a cathode ray tube. So if you have an old TV lying around, now we have flat screen LCD panels, but monitors, video monitors, used to be cathode ray tubes, and so you'd have to charge parallel plates like this and then shoot electrons through them in order to light up certain parts of a screen. And so this set of parallel plates would direct the electrons where they needed to go. So it was a very useful piece of technology when it was common. It's no longer common, right? So now it's just really not used for much. But it will be useful for when we talk about how circuits work as well. Okay, but we're starting with something that we've already discussed in grade 11 so that we can hopefully make that connection a little bit easier. So when we send an electron into here, it's going to get pushed, right? The negative pole or the negative plate is going to push that electron this way. So there's some pressure on this electron. Okay, so over here we have an area of high potential. Over here we have an area of low potential. And when we put an electron over here, it has high potential energy. And when we put an electron over here, it has low potential energy. This is very much like how a water system works. Let's look at it like this. We have a water pipe and a pump, and this pump is going to push water around a circuit like this. Okay, so this is a reservoir here. It's just unlimited water. This is a reservoir. Okay, so when you turn the pump on, let's say you haven't opened this. When you turn the pump on, it has a certain amount of pressure that's available to it. Okay, that pressure, water pressure, is like voltage in an electrical circuit. Okay, right now it's got no water flowing through it, but if we get rid of that blockage there, now it's going to pull water into the circuit, and this water is going to flow through from here all the way around this edge here, and then it's going to flow back in to the pump again to be circulated once more. Okay, over here the water has a very high pressure. Okay, let's say it's, I don't know, 75 pounds per square inch. As it goes through the circuit, it is losing pressure. And then once it makes it all the way back to here, it's got negligible pressure. Right over there would be 0 pounds per square inch. I notice this in my house because upstairs, when you are taking a shower, if you're also running water downstairs, your water pressure suffers quite a bit because our water system can't push water all the way upstairs as well as it can push water to the main floor. Okay, so it's the same with voltage. This pump is able to provide a certain amount of voltage or pressure at the beginning, and that voltage is what pushes electrons around a circuit, or in the case of parallel plates, that voltage is what pushes electrons to the other side. Okay, And as you move from one side to the other, or as you move around the circuit, that voltage diminishes. The location is changing. So here's location number 1, and that has the highest voltage. Over here, it's going to have lower voltage, lower voltage, lower voltage, lower voltage, just like water pressure.